In section 5.2, we'll be looking at systems of linear equations in 3 variables. Our objectives will be to identify solutions to systems of linear equations, solve systems of linear equations in 3 variables, and use systems of linear equations in applications. So what we'll be looking at today is systems that have 3 variables. Those variables are usually x, y, and z, and there is a way to draw this in space instead of just in a plane with x and y. So let's take a look at example 1. Determine if 5, 3, negative 2 is a solution to this system. So if we want to know if this is a solution to this system, first recognize that we have an ordered triple in the form of x, y, and z. This ordered triple will be a solution to this system if it satisfies all 3 of these equations. If it fails to satisfy one of them, then it is not a solution to the system. And so all we do is we check each equation. So I'm going to plug in 5 for x, 3 for y, and negative 2 for z in that first equation. So we get 2 times 5 plus 5 times 3 minus negative 2. And I'm going to work this out to see if it is equal to 27. 2 times 5 is 10. 5 times 3 is 15. And a negative 2 is a positive 2. And sure enough, 10 plus 15 plus 2 is 27. So the first equation does work out. And then we check the second equation. So it'll be 4 times the x value of 5 minus 3, the y value, minus 2 times the z value, negative 2. Let's work this out to see if it is equal to 21. So 4 times 5 is 20, minus 3, negative 2 times negative 2 is positive 4, and yes, 20 minus 3 is 17, plus 4 is 21. The second equation works. And lastly, let's check the third equation. 5 times the x value of 5. Notice that there is no y in this last equation, so there's no place to put the 3. That was y equals 3. We move on to plus 3 times z, which is negative 2. And we get 25 minus 6 is indeed equal to 19. So since this ordered triple of 5, 3, and negative 2 satisfies all 3 of the equations, we say that 5, 3, negative 2 is a solution to the system. Next, let's look to see how to solve a system of equations. There are several steps that you need to do. First, write each equation in the standard form. Next, choose a pair of equations and eliminate one of the variables by using the addition method. Next, choose a different pair of equations and eliminate the same variable that you eliminated from the previous step. Once you've eliminated one of the variables, you'll now have 2 equations with 2 variables. And this goes back to our previous knowledge. We know how to eliminate and solve when we have 2 variables with just 2 equations. You'll solve those 2 equations for the 2 variables, and then you can use that information to plug it in to one of the original equations to find the third variable. Lastly, you should check the ordered triple in each of the original equations to see if it is a solution, and then write that in set notation. Let's take a look at example number 2. Solve this system. So first thing we notice is that all the equations are in the standard form. So next, I'm going to pick a pair of equations to work with. So I'll pick the first equation. So 3x plus 4y plus z is equal to 7. And I'll pick the middle equation, negative x plus 2y plus 3z is equal to 1. We're going to solve this as a system using addition-elimination method. So I want to eliminate the x. So let me put that here. I'm going to get rid of x. And I chose that because I can see that I already have 3x right here and negative x here. So you have to multiply the second equation by some number in order to get rid of the x when it combines with the 3x. This is one of the easier ones to do. I'm going to multiply the bottom equation by 3. When I do that, the top equation stays the same. And the bottom equation, I multiply every term by 3. That gives me negative 3x, positive 6y, positive 9z is equal to 3. Then I can add these equations down, and the x's will cancel. The y's, I would get 4y plus 6y is 10y. 1z plus 9z is 10z. And 7 plus 3 is 10. So I've eliminated x, and I end up with the equation 10y plus 10z equals 10. You can also simplify this equation by multiplying everything by 1/10. You do not have to do this, it's not imperative, but it will make the equation just slightly easier. Multiplying by 1/10 changes all the coefficients and the number to 1. Let's keep this equation in mind. I'm going to put a little box over it. It's not the solution, but I'm going to keep that in mind. And then we come over and we need to choose a different pair. I'm going to choose the second equation again. Negative x plus 2y plus 3z equals 1. And since I picked that one, I have to choose the bottom one. So 6x plus 5y plus 9z equals negative 9. Again, I have to eliminate x. I have to eliminate the variable from the first pair. I have to eliminate that same variable over here. So if I'm going to eliminate x, I need to get this top equation to be negative 6x to eliminate with the bottom one. So I'm going to multiply both sides by a 6. This gives me negative 6x plus 12y plus 18z is equal to 6. And the bottom equation stays the same. 6x plus 5y plus 9z equals negative 9. Next, I add these equations straight down. The x's cancel, and that leaves me with 17y plus 27z is equal to negative 3. This is my second equation that I need to use going forward. Nothing reduces in that one. Now, let's solve these two equations together. So I have y plus z is equal to 1, and 17y plus 27z is equal to negative 3. I'm going to solve this one using substitution. So solving the first equation for z, I get that z is equal to 1 minus y. That tells me that the next equation is actually 17y plus 27 times 1 minus y is equal to negative 3. Simplifying, I get 17y plus 27 minus 27y, since the 27 distributes, is equal to negative 3. Combining like terms, I get negative 10y is equal to negative 30. And then y is equal to 3. So that is one of the solutions that I need. I can substitute this y into my equation with z, and that tells me that z is equal to 1 minus 3, which gives me z is equal to negative 2. And finally, I need to solve for x. I'll use the middle equation, which was negative x plus 2y plus 3z is equal to positive 1. And I will substitute what I know about y and z. So I get negative x plus 2 times 3, since y was 3, plus 3 times the z value of negative 2. That's equal to 1. And in this case, we have a 6 and a negative 6 on the same side of the equation. Those cancel. That gives me negative x is equal to 1, and x is equal to negative 1. So the ordered triple, that is the solution to this system, is negative 1, comma 3, comma negative 2. Let's take a look at example 3, solve this system. So once again, I'll pick a pair of equations to start working with here. I'll pick the top one, 9x minus 2y minus 12z is equal to 11. And I'll pick the middle one, 2x minus y minus z is equal to 3. There's a couple of good choices for eliminating here, but I'm going to choose to eliminate y. So let me make a note of that. Eliminate y. And to eliminate the y, I need to multiply the bottom equation by negative 2. And the top equation stays the same, 9x minus 2y minus 12z is equal to 11. The bottom equation becomes negative 4x plus 2y plus 2z is equal to negative 6. Add the equations to eliminate the y's, and we get 5x. The y's are eliminated. And let's see, minus 10z is equal to 5. Here again we have an equation that we can reduce. I'm going to reduce this one by multiplication by a fifth. And again, not necessary, but sure does make the numbers a little smaller. And that would give us x minus 2z equals 1. All right, then I pick another pair, and I'll pick the second and third equations. So 2x minus y minus z equals 3, and 3x minus 2y equals 5. Again, I have to eliminate the y, so I'm going to multiply the top equation by negative 2. And that gives me negative 4x plus 2y plus 2z is equal to negative 6. The bottom equation stays the same. The y's are eliminated, and the x's become negative x plus 2z is equal to negative 1. So this is the second equation that I will use. Next, let's put these two equations together to solve. So we would get x minus 2z is equal to 1, and negative x plus 2z is equal to negative 1. Notice that I could use addition to eliminate the x's, and the x's here would be canceled. However, notice that whenever I do that, I also eliminate the z's. I have negative 2z and positive 2z, and that leaves me with 0 on the left. What does that leave me with on the right? Well, it eliminates the 1 and the negative 1 as well, which is equal to 0 as well. This is a true statement, but all the variables have been eliminated. That tells me that there are infinitely many solutions. And we say that these equations are dependent. So since I did get a true equation without any variables, 0 equals 0, it's infinitely many solutions and the equations are dependent. Now, had you ended up with 0 equals another number like 4 or so, something like this, then there would be no solutions because that would be a false statement. Let's take a look at some of the applications of a system with 3 variables. Example number 4, find the equation of the quadratic function that passes through the points negative 4, negative 21, negative 1, 3, and 3, 7. So first let's recall what the quadratic functions look like. So a quadratic function is a function that's in the form of y equals ax squared plus bx plus c. And in order to find the exact equation of the quadratic function that's going to pass through these 3 points, I just need to identify what the a, the b, and the c should be. Well, let's create 3 equations here. I'm going to use each of these points separately. So by starting with the point negative 4, negative 1, we know that the y value is negative 21. And that is the result of plugging in negative 4 into the equation with x. And so we will get a times negative 4a, negative 4 squared, rather, plus b times negative 4 plus c. And then I repeat this for the other 2 points. So the point -1, 3 is a y value of 3 when the x value is -1. So it's a times -1 squared plus b times -1 plus c. And the point 3, 7 is 7 is equal to a times 3 squared plus b times 3 plus c. And now we're going to take these three equations and turn them into the system that I want to use to solve for a, b, and c. So the system would be 16a minus 4b plus c is equal to -21. -1 squared is +1, so that's 1a minus b plus c is equal to 3. And the last equation, 3 squared is 9, so that's 9a plus 3b plus c equals 7. And now I use the methods that we've already talked about to solve this system for a, b, and c. So to solve, I'll pick the first equation and the second equation. And I'm going to multiply the second equation by -16. And I want to eliminate the a. So the first equation stays. The second equation becomes -16a plus 16b minus 16c equals -48. When I add down, the a's are eliminated. That leaves me with 12b minus 15c equals -69. Let's hold on to that equation. Then I will choose the second equation and the third equation, and that would be a minus b plus c is equal to 3, and 9a plus 3b plus c equals 7. To add and eliminate this, I'm going to multiply the top equation by -9. That gives me -9a plus 9b minus 9c equals -27. And then 9a plus 3b plus c is equal to 7. Elimination here gets rid of the a's. And we are left with 12b minus 8c is equal to -20. Let's keep that equation in mind. And now use those two together to continue the process of solving. So we have from the first section 12b minus 15c equals -69. And 12b minus 8c is equal to -20. to be able to add and eliminate, I'm going to multiply the bottom equation by -1 to eliminate the b's. That leaves me with 12b minus 15c equals -69. And -12b plus 8c is equal to +20. When I add these down, the b's are eliminated, leaving me with -7c is equal to -49, which then gives me c is equal to 7. So we have the c value. C is equal to 7. I can now back substitute into either one of these equations here. I'll just use the first one. Doesn't matter, either one. I'll take 12b minus 15 times 7 is equal to -69. 12b minus 15 times 7 is 105, which is equal to -69. 12b is equal to 36 after you move the -105 to the right side. And so b is equal to 3. Substituting b and c into any of the original equations, we can find the value of a. So I'll just pick this one here. A minus b plus c is equal to 3. Gives me a minus 3 plus 7 equals 3, which tells me that a is equal to -1. And for this problem, it's not enough to know what the a, the b, and the c are. We are tasked with finding the equation of the quadratic function that passes through those points. So the answer is going to be y equals ax squared plus bx plus c with the a, b, and c that we found. So y is going to equal to -x squared plus 3x plus 7, where I have plugged in the a, the b, and the c. Let's take a look at this example. Example number 5. A movie theater showed a new animated film. They sold a total of 169 tickets to adults, children, and seniors. The ticket prices for adults, children, and seniors are $8, $4, and $3 respectively. The total sales from these tickets equaled $915. Also, the total number of adult and senior tickets sold was 7 less than the number of child tickets sold. How many tickets of each type were sold? So first, let's start by declaring our variables. So let's let A equal the number of adult tickets sold. Let C equal the number of child tickets sold. And S equal the number of senior tickets sold. Next, using these variables, we want to create the 3 equations that were mentioned in the word problem. The first one is they sold a total of 169 tickets. So I'm going to take the number of adult tickets, A, plus the number of child tickets, C, plus the number of senior tickets, S, and that should equal $169. Next, the sentence is, the ticket prices for adults, children, and seniors were $8, $4, and $3 respectively. The total sales from these tickets equaled $915. So if I can take the total revenue from adult tickets, the total revenue from child tickets, and the total revenue from senior tickets, and add all that together, I should get $915. So the question then becomes, how much money did we make from adult tickets? Well, we sold A adult tickets, and they cost $8 each, so the revenue from adult tickets is 8A, the price times the number sold. Same thing for the child tickets. Child tickets cost $4, and we sold C of them, so the revenue from child tickets is 4C. And finally, for seniors, $3 a ticket, we sold S of them, so it's 3S. And that total is $915. Finally, we need one more equation since we have three variables. And the sentence is, the total number of adult and senior tickets sold was 7 less than the number of child tickets sold. So we have the number of adult tickets plus child tickets was equal to, The total number of adult and senior tickets sold was 7 less than the number of child tickets sold. How many tickets of each type were sold? So we have the number of adult tickets plus senior tickets is equal to child tickets minus 7. All right. So let's go ahead and solve this system using our techniques from before. So one, I'm going to pick the first and second equations to solve. So A plus C plus S is equal to 169, and 8A plus 4C plus 3S is equal to 915. I'm going to multiply the top equation by -8 so that I can eliminate A. And that gives me -8A minus 8C minus 8S is equal to -1,352. The second equation stays the same. Next, add down. The A's will cancel as desired, and that leaves us with -4C minus 5S is equal to -437. All right, let's hold on to that one for a moment. And I'll scroll back to look at the system here. The next equation I want to work with is the top equation, A plus C plus S is equal to 169, and I want to work with the bottom equation. However, notice the bottom equation is not in the standard form. So as I rewrite the equation, I'm going to put it in standard form as I go. It'll be A, I'm going to move the C over and it becomes -C plus S is equal to -7. To solve this equation and to eliminate the A, I'm going to multiply the bottom equation by -1. This gives me A plus C plus S equals 169. And the bottom equation is now negative A plus C minus S is equal to positive 7. When we add down, we eliminate A, and we get 2C. However, in the process of eliminating A, we also eliminated the S, which is fantastic. It does save us some work. 169 plus 7 is 176. Divide both sides by 2, and we get that C is equal to 88. So we actually have the solution right there. Without going to the third step, we did get one of the variables. Fantastic. Now I can take this value of C and plug it into this equation in the green box. And we get negative 4 times 88 minus 5 times S is equal to negative 437. That gives me 5S is equal to negative 85. And S is equal to 17. So the number of seniors was 17. And then finally, to solve for A, I can plug it into any of the equations. I prefer to plug it into the one about tickets. So A plus C plus S is equal to 169. So A plus 88 plus 17 is equal to 169, which means A is equal to 64. Double check the reasonableness of your answer. Since this is an actual application with tickets, you know that the number of tickets sold can't be negative, and none of our answers are negative. And they also have to be positive integers. You can't sell a half a ticket. So all three of our answers check on that front, and so this is a good answer. Thanks for watching.